Section: Introduction. In this section, we discuss the advancements in text-based diffusion models that have successfully generated images and videos by utilizing larger datasets and computational power. However, we face significant challenges in effectively controlling these models. The gap between natural language and visual representation makes it difficult to accurately describe the positions and characteristics of multiple objects, often resulting in confusion. Consequently, these models perform better with simpler images that feature fewer dominant elements. To evaluate the capabilities of the leading text-to-image generation system, DALL-E3, we employ instance grids inspired by the Chihuahua or Muffin test, which assesses visual recognition in multimodal language models. We organize region positions and their captions into structured sentences. Our findings reveal that DALL-E3 struggles with generating accurate results in a 9-grid format, underscoring the limitations of relying solely on language for controlling visual elements. Similar to the evolution in visual recognition, which has moved from focusing on single objects to recognizing them in complex settings using bounding boxes, visual generation is also adapting to use bounding boxes for controlling regions of interest. However, a key difference is that visual generation must manage variable-sized regions on high-resolution feature maps. For instance, while faster RCNN processes lower-resolution features, generative models work with higher-resolution features, often requiring more complex computations. We categorize previous methods for instance control into two main approaches. 1. Implicit ROI injection through embedding, where regional information is combined with instance captions using self-attention. This method avoids direct handling of variable-sized regions but suffers from attribute leakage and poor spatial alignment. 2. Explicit ROI injection with attention masks, which isolates each region during caption injection, improving spatial alignment but still incurring high computational costs. In our work, we propose a new strategy for instance control in visual generation. We introduce ROI unpool, an operation that restores cropped region features to their original positions on high-resolution maps. By combining ROI align and ROI unpool, we enable efficient extraction and processing of region features without being dependent on the original feature size. We also present ROICtrl, an adapter that integrates instance control into existing diffusion models, compatible with both spatial and embedding-based add-ons, thus broadening their use for generating multiple instances. To evaluate instance control, we note that previous benchmarks primarily used template-based captions, which limited their scope. To fill this gap, we introduce ROICtrl Bench, a benchmark designed to assess both template-based and free-form captions, leveraging the capabilities of multimodal language models for a more thorough evaluation. In summary, our contributions include the introduction of ROI unpool for efficient ROI injection, the ROICtrl adapter for existing diffusion models, and the ROICtrl Bench for comprehensive evaluation of instance control. Our approach demonstrates state-of-the-art performance and improved efficiency across various benchmarks. In the next section, we will explore related work in controllable visual generation, highlighting the limitations of current models in capturing detailed spatial and identity information. Section Summary. In this section, we discuss the challenges of controlling text-based generative models for visual content, highlighting the limitations of current methods in accurately managing multiple instances due to linguistic ambiguity and computational inefficiencies. We introduce our innovative approach, ROICtrl, which utilizes a new operation called ROI unpool to enhance instance control in visual generation, along with a benchmark, ROICtrl Bench, to evaluate its effectiveness against existing methods. Section: Instance control in visual generation. In this section, we discuss instance control in visual generation. Unlike other controls that focus on precise visual alignment, instance control allows us to manage different instances independently, preventing any overlap of attributes between them. This method is often linked to bounding box, layout, or region control, which we collectively refer to as instance control. We begin with training free instance control, which adjusts the attention map in diffusion models during inference. This approach is based on the idea that cross-attention carries layout information. We aim to strengthen the impact of nouns on their respective areas using techniques like attention modulation or latent optimization. However, this method can lead to a compromise between image quality and spatial alignment, along with higher computational demands and less flexibility during inference. Next, we explore training-based instance adapters, which learn instance control from data. These can be split into implicit and explicit injection methods. Implicit injection encodes bounding box coordinates as positional embeddings, merging them with instance caption embeddings. A gated self-attention mechanism then integrates the instance embedding into spatial features. While this avoids the complexities of handling variable-sized regions of interest, ROIs, it often results in poor spatial alignment and significant attribute leakage. On the other hand, explicit injection focuses on the target area during instance caption injection, reducing attribute leakage. Previous methods have used attention masks to eliminate unrelated regions, but this leads to excessive computation and errors in coordinate quantization. To overcome these issues, we propose ROICtrl for efficient and precise ROI injection. We also touch on instance recognition in visual understanding. Early studies concentrated on object classification, typically involving a single prominent object per image. As the field evolved, the focus shifted to detecting multiple objects in context, using bounding boxes for individual object localization. The two-stage detector is a key method in object detection, utilizing ROI pool or ROI align to streamline feature extraction from variously sized ROIs. Inspired by this research, we investigate effective ROI operations for visual generation. In our methodology, we first define the problem of multi-instance generation. We then introduce the basic operation, ROI unpool, followed by a description of the ROICtrl adapter design. Finally, we discuss the applications of ROICtrl. For problem formulation, we define multi-instance generation as using a global caption to describe the entire image, along with individual instance captions and their corresponding bounding box coordinates for each instance. Our goal is to create an adapter that integrates region-specific information into a pre-trained diffusion model, achieving strong spatial and regional text alignment. Additionally, we emphasize the importance of free-form instance captions for flexibility and compatibility with fine-grained controls, as bounding boxes alone provide limited spatial cues. Regarding ROI unpool, we note that visual generation requires processed ROI features to be accurately placed back at their original coordinates on the spatial feature map. Existing methods often use a masked attention mechanism to zero out unrelated areas during instance caption injection, which maintains the original spatial coordinates of each ROI. However, this method incurs significant redundant computation and coordinate quantization errors. To tackle the challenges of accurately placing varied-sized ROIs back onto their original coordinates, we introduce ROI unpool, which works alongside ROI align. Specifically, while ROI align computes ROI features by resampling from the nearest grid points, ROI unpool reconstructs spatial features using the nearest grid points from the ROI feature, leaving empty spaces for areas not corresponding to the ROI. Section Summary. In this section, we discuss instance control in visual generation, which allows for independent manipulation of different instances while preventing attribute leakage. We introduce methods such as training free instance control that enhances attention maps during inference, and training-based instance adapters that incorporate region-specific information, culminating in our proposed ROI unpool technique for efficient and accurate ROI operations. Section ROICtrl. In this section, we introduce ROICtrl, an adapter that integrates instance captions into diffusion models, building on ROI unpool. As shown in our figure, ROICtrl adds an instance caption injection alongside the existing global caption injection. We combine the outputs from global and instance attention using a learnable blending method. Specifically, when we have a global caption and multiple region captions with their coordinates, ROICtrl aims to inject these conditions into the spatial feature, resulting in a modified feature. In ROICtrl, the global caption gives an overview of the image, while the instance caption details each specific instance. We utilize pre-trained cross-attention from the diffusion model to generate the global attention output. For instance caption injection, we extract the region of interest, ROI, features from the spatial feature using ROI align. We then apply the pre-trained cross-attention to inject the instance captions into each ROI feature without adding new learnable modules, which helps maintain the pre-trained model's knowledge and compatibility with other embedding methods. To avoid artifacts from directly applying cross-attention to ROI features, we introduce ROI self-attention to refine these features. Finally, we place the refined ROI features back into their original positions in the feature map to create the instance attention output. For learnable attention blending, we concatenate the global and instance attention outputs along the ROI axis to form a combined output. Our goal is to dynamically adjust the importance of these outputs at each spatial location. We calculate learnable fusion weights by applying a small convolution to reduce the channel dimension and then use a softmax function across the ROI axis. These weights allow us to perform a weighted fusion of the combined attention output, resulting in the final attention output. We also incorporate instance box embeddings to guide occlusion scenarios, using only box embeddings to avoid attribute leakage, which enhances objectness in the relevant areas. We optimize ROICtrl using the standard diffusion loss, with an additional regularization applied to the fusion weights to minimize the global attention output's influence within the ROI and improve alignment with the instance captions. The regularization term is based on a mask that identifies the foreground area containing the ROI. Our final objective function combines the diffusion loss with the regularization term, maintaining a consistent value for the regularization weight throughout our experiments. Section Summary. In this section, we introduce ROICtrl, an adapter that integrates instance captions into diffusion models by fusing global and instance attention outputs through a learnable blending mechanism. We also describe our training objective, which combines standard diffusion loss with a regularization term to enhance spatial alignment and reduce the influence of global attention within regions of interest. Section Application. In this section, we discuss the applications of ROICtrl. First, we can use ROICtrl for instance control in complex compositions without any extra tools. Each instance can be described using free-form text, as shown in our first figure. Next, once we train ROICtrl on a base model, it can easily adapt to various community models that have been fine-tuned from that base model, which we illustrate in our second figure. ROICtrl also works well with spatial-based add-ons. It helps separate different instances and can collaborate with detailed spatial controls, like ControlNet and T2I adapter, during inference. Our third figure shows that T2I adapter alone struggles to control specific instances and suffers from attribute leakage without ROICtrl. Additionally, ROICtrl is compatible with embedding-based add-ons, allowing us to manage instance identity. Our fourth and fifth figures demonstrate that it supports both tuning-based ED-LoRa and tuning-free IP adapter. This compatibility is achieved by reusing pre-trained cross-attention, avoiding the need for new learnable modules for instance captions, which ensures smooth integration with embedding-based add-ons. We also enable continuous generation with ROICtrl, allowing us to modify local areas while keeping previously generated content intact, as shown in our sixth figure. For our experimental setup, we implement ROICtrl using the PyTorch framework and create a custom CUDA kernel for the ROI unpool operation to improve efficiency. We define the size of the region of interest, ROI, based on a specific formula related to the spatial feature size. For instance, if our diffusion model works at a resolution of 512 by 512, we calculate the corresponding ROI sizes based on the feature resolutions. We train our model on the MS-COCO dataset, recaptioning each instance with free-form text generated by CogVLM. Our training involves a batch size of 128 and a learning rate of 0.00005, conducted over 60,000 steps using 8 NVIDIA A100 GPS. For evaluation, we create ROICtrl bench. Existing benchmarks mainly focus on template-based instance captions, but we recognize that users need free-form captions for a wider range of attributes. To address this, we designed ROICtrl bench with 4 tracks. The first 2 assess template-based captions, while the last 2 evaluate free-form captions, including the model's ability to generate out-of-distribution captions using GPT-4. We evaluate instance control based on 2 main criteria: spatial alignment and regional text alignment. For spatial alignment, we report the mean intersection over union, MIOU, calculated by detecting region proposals and matching them with ground truth boxes. For regional text alignment, we check if cropped regions of the generated image match their instance captions using Mini CPMV 2.6, reporting the match rate as accuracy. In our quantitative comparison, we find that ROICtrl outperforms both instance diffusion and MIGC in generating small objects due to its precise localization, as shown in our results. Although ROICtrl performs slightly worse than instance diffusion on out-of-distribution subjects, it still shows superior spatial and regional text alignment compared to previous methods. In our qualitative comparison, we observe that ROICtrl effectively handles occlusions when bounding boxes overlap. It also demonstrates less attribute leakage with out-of-distribution instance captions compared to GLIGEN and MIGC, while maintaining better global consistency than instance diffusion. Furthermore, ROICtrl achieves better regional text alignment with free-form instance captions than earlier methods. Section Summary. In this section, we explore the diverse applications of ROICtrl, highlighting its ability to control instances in complex compositions using free-form text, adapt to various community models, and collaborate with both spatial and embedding-based add-ons for enhanced instance identity control. We also discuss our experimental setup, evaluation metrics, and demonstrate that ROICtrl outperforms prior methods in generating small objects and maintaining spatial and regional text alignment. Section: Compare to ROI injection via embedding. In this section, we compare ROICtrl with embedding-based ROI injection, which we refer to as GLIGEN**. Our findings, illustrated in the accompanying figure, show that ROICtrl consistently outperforms GLIGEN** even after significantly more training steps. Notably, GLIGEN** struggles with spatial alignment, particularly after 500,000 training steps. It also faces issues with regional text alignment due to its use of global self-attention, which leads to attribute leakage. Furthermore, embedding-based ROI injection has difficulty generalizing when the aspect ratio during inference differs from that used in training, as demonstrated in another figure, making it less suitable for practical applications requiring flexibility. Next, we compare ROICtrl with attention mask-based ROI injection. We modified ROICtrl by replacing certain components with masked attention, resulting in a variant we call ROICtrl mask. While this variant achieves similar regional text alignment, it suffers from poorer spatial alignment, requires more training memory, and slows down inference. We also compared ROICtrl with previous methods like instance diffusion and MIGC. Instance diffusion is more computationally demanding, while ROICtrl offers a significant speed advantage. MIGC reduces computation by using adapters on low-resolution features, but this leads to degraded performance and is still slower than ROICtrl. Both instance diffusion and MIGC depend on learnable modules for regional caption injection, which makes them incompatible with certain embedding-based add-ons. We then discuss key design choices in ROICtrl. First, we note the effect of ROI self-attention. We utilize pre-trained cross-attention for injecting instance captions, but without refining it with ROI self-attention, we see a drop in spatial alignment. Removing ROI self-attention significantly decreases performance metrics on our benchmarks. Next, we examine the role of the regularization term, L_reg. This term helps reduce the influence of global attention within the ROI. Omitting it leads to poorer regional text alignment, as shown by declines in accuracy metrics. Our visualizations indicate that applying L_reg improves the textures of certain objects. We also compare global coordinate conditioning, used in ROICtrl, with regional coordinate conditioning found in recent works. While local conditioning shows slightly better performance in controlled settings, it does not generalize well to varying resolutions in real-world applications, leading to issues like subject repetition. Finally, we implement multi-scale ROIs in ROICtrl to adapt to the multi-scale feature maps of UNet. Our comparisons reveal that multi-scale ROIs provide better spatial alignment while maintaining similar text alignment compared to single-scale ROIs.